Welcome! In this lecture you will learn about the humidification process, the wet bulb temperature and evaporative cooling. They all three relate strongly to each other. Let's start with evaporative cooling. You have learned already that as long as the partial pressure of the water vapor is below the saturation pressure, water can evaporate in air. To evaporate this water, heat is needed, the latent heat of evaporation. The water droplets take this heat from the air itself, which therefore cools down. With this heat, the droplets vaporize and mix with the air. So, on the left, we have dry, warm air with water droplets coming in, leading to colder and more humid air. There have been no heat exchange with the outside of the system. No heater or cooler was applied. Heat has only been exchanged within the air and the water. We call this an adiabatic process. It costs no energy. The wet bulb temperature relates strongly to this adiabatic process. By definition, the wet bulb temperature of air at a certain pressure, temperature T1 and absolute moisture content X1, is the saturation temperature TWB that the air would achieve when absorbing adiabatically as much water as needed to reach saturation under the condition that the water is already at wet bulb temperature. The picture illustrates the definition. You see that the water is at TWB and that this water is injected into the incoming air, which goes out of the pipe in saturated state TWB-X2. There is a fan on the right to help the air to circulate. There is no heat exchange with outside because the pipe is perfectly insulated, which is what is called an adiabatic process. Let's look at a mass of 1 kg dry air. The water content at the outlet is X2, the one at the inlet is X1, so the difference, X2 minus X1, has been injected. In the figure, XW equals X2 minus X1. Let's make an energy balance. The total enthalpy of the incoming humid air is H1 kJ per kilogram dry air. You learned in another lecture how to calculate it. The enthalpy of liquid water at TWB is the mass of water, which is X2 minus X1, times C of water times TWB. So H1 plus X2 minus X1 times C times TW must be equal to H2. In general, the term X2 minus X1 times C times TWB is very small compared to H1, by which H2 is almost equal to H1. And that is what we see in the Mollier diagram. The lines of constant wet bulb temperature TWB are these diagonal dotted lines in the Mollier diagram that seem to be parallel to the isenthalpic lines. You see here the wet bulb line 25 degrees. You can observe that it crosses the saturation line at a dry bulb temperature of 25 degrees too. Let's show now the wet bulb line for 15 degrees here. Note that the temperature is written just above the line close to the saturation line. The dry bulb temperature is 15 too. At 0 degrees it is here, etc. I said it already, the lines of constant wet bulb temperature seem to be parallel to the isenthalpic lines, but they are not completely. If you would zoom in, we would see this, just as we derived in the previous slide. Practically, at the temperature and pressures we are working with, we cannot really make difference on the diagram, and the wet bulb temperature determined using the isenthalpic lines or the wet bulb temperature lines will be very similar. If you want to make calculations to determine the wet bulb temperature TWB and humidity X2 corresponding to point 1 with temperature T1 and humidity X1, you have to start from the equation we just studied and replace the enthalpies by their formulas as you learned to do in the lecture about enthalpy. If you reorganize the equation in order to have the unknowns X2 and TWB on the left, you get this. There are two unknowns, so we need a second equation to determine these unknown parameters. Maybe you remember a lecture about psychrometric carts and humidity, in which we derived the relationship between saturation pressure and temperature, and the relationship between partial pressure and absolute humidity. On the saturation line, PW equals PWS, which leads to this second equation. By combining 1 and 2, you should be able to determine the wet bulb temperature TWB and the corresponding absolute humidity. It is quite easy to measure the wet bulb temperature using a device similar to the one we studied 3 slides ago. In fact, the wet bulb temperature is the temperature a thermometer would take when wrapped in wet cloth and put in an airflow with a certain temperature T1 and absolute humidity X1. The wet cloth has to remain wet all time, so it must be continuously wetted by water, like in this instrumental setup. The wet bulb lines on the Mollier diagram show the combinations of temperature T1 and absolute humidity X1 leading to a specific wet bulb temperature. If we look again at the figure on the left and we add in the box a thermometer measuring the temperature of the air, the dry bulb temperature, we can then determine very interesting properties. The crossing point of dry bulb and wet bulb temperature tells us what are the absolute humidity and relative humidity of the air. Such an experimental setup is called a psychrometer. In my example, in the Mollier diagram, you see that the psychrometer has measured a wet bulb temperature of 15 degrees and a dry bulb temperature of 26 degrees Celsius. The line of constant dry bulb temperature goes like that, and the one of constant wet bulb temperature like that. Their intersection determines a unique point on the Mollier diagram that gives us the absolute humidity of the air, 6.5 grams in our case, and the relative humidity 30%. That's how humidity is measured. Let's now look at adiabatic humidification and evaporative cooling. Let's take the example of humid air at 22 degrees Celsius and an absolute humidity of 1.8 grams per kilogram, corresponding to a relative humidity of 10%. This humidity may be a bit low to ensure comfort. You may remember from other courses that a minimum humidity of 30% is recommended to avoid electrostatic shocks. This can very easily be achieved by injecting water droplets in the air until the moment the right humidity is achieved. The process takes place along the constant wet bulb temperature line, which is also an adiabatic line, until 30% humidity is achieved. At that point, 1 kilogram dry air contains 3.8 gram water vapor, meaning that during this process 2 grams of water have been added. During this process, the air temperature has decreased from 22 to 17 degrees Celsius. Evaporative cooling works exactly the same way, with now cooling as main perspective. Let's take humid air at 30 degrees Celsius and an absolute humidity of 10 grams per kilogram, corresponding to a relative humidity of 38%. This temperature is too high to ensure comfort. The air can be cooled easily to 25 degrees, for instance, by injecting water droplets until the moment the right humidity is achieved. The process takes again place along the constant wet bulb temperature line until 25 degrees is achieved. At that point, 1 kilogram dry air contains 12 grams water vapor. During this process, the relative humidity has increased to 60%. Let's look now at these processes in the psychrometric cart and take again the example of humid air at 22 degrees Celsius and an absolute humidity of 1.8 grams per kilogram, corresponding to a relative humidity of 10%. To achieve a relative humidity of 30% by injecting water droplets in the air, we have to follow the line of constant wet bulb temperature, which is here, until 30% humidity is achieved. At that point, 1 kilogram dry air contains 3.8 gram water vapor, meaning that during this process 2 grams of water have been added. And we also see that the temperature of air has decreased from 22 to 70 degrees. Instead of humidifying air with water droplets, it is possible to use steam, which is water vapor at temperatures above 100 degrees Celsius. As steam is hot when injected in air, it is likely that air will be heated or at least cooled much less than when using adiabatic humidification. Let's look at the enthalpies. Similar to adiabatic humidification, the enthalpy at point 1, the original state, plus the enthalpy of the steam equals the enthalpy at point 2, the final state. And the total mass of water vapor after humidification, X2, is the sum of the original mass and the added steam. So X2 is X1 plus X steam. The enthalpy of saturated steam at a certain boiling temperature T steam is the energy content of water at this temperature, which is the specific heat of water times the boiling temperature plus the latent heat of evaporation at this temperature. The specific heat of water is 4.18 kJ per kilogram, and as for the latent heat of vaporization of water, QL, you can find it easily in tables like this one. You can easily determine the enthalpy at point 1, H1, which is given here, as we have studied earlier. H2 can then be calculated as the sum of H1 and the enthalpy of the added steam. Once you know H2, you can determine T2 using the formula for the enthalpy. Let's take an example of 5 grams of steam at 100 degrees being injected into air at 22 degrees and absolute humidity 1.8 gram per kilogram dry air. The latent heat of vaporization of steam at 100 degrees is 2257 kJ per kilogram. The enthalpy of steam is therefore 4.18 times 100 plus 2257 equals 2675 kJ per kilogram. X2 is X1 plus X steam equals 5 plus 1.8 is 6.8 gram. Using the last equation in black, we can derive that T2 is then 22.7 degrees Celsius. The air temperature has increased a little bit, but not that much. How to use the Mollier diagram to find the conditions at point 2? Well, this is the only case where you need to make a small calculation before using the diagram. You need to calculate on beforehand the specific enthalpy of the steam, H steam in kilojoule per kilogram steam, as we did on the slide before. H steam is 4.18 times temperature plus the latent heat. In the Mollier diagram and the psychrometric chart, H steam is called delta H over delta X. Let's take again the example of the injection of 5 grams steam at 100 degrees in air at 22 degrees and humidity 1.8 gram per kilogram. So, point 1 in the diagram is here. Because of the conservation of mass, we know on which vertical line the final point should be. X2 is 1.8 plus 5 equals 6.8 gram. With the help of the table in previous slide, we can calculate H steam, which is 2675 kJ per kilogram. The dH over dx scale is here. Lines start from 0, so we draw here the line corresponding to dH over dx is 2675. After that, we just draw a line parallel to this one, but starting from point 1, like this. Where the two lines are crossing, we find the final point, 2, corresponding to a temperature of approximately 22.7 degrees. Note that the process of injecting steam at 100 degrees is almost isotherm. The temperature changes only a little bit. But of course, the warmer the steam, the warmer the final temperature. If we look at the process in the psychrometric chart, we plot here again point 1 and then the line of constant absolute humidity as 6.8 gram. Then we need to go first to the protractor above and draw here from the point in the middle the line of dH over dx is 2675, expressed in the protractor as 2.7, so divided by 1000. We draw then a line parallel to this one, but starting from point 1. At the intersection, we'll find the final point 2. To summarize this lecture, you have learned that the wet bulb temperature lines describe an adiabatic process, which is the process followed by evaporative cooling, which is the same as adiabatic humidification. During such a process, there is no heat exchange with outside, the air humidity increases and the temperature decreases. You are also aware that air humidity can be measured by measuring both the dry bulb and the wet bulb temperatures. And finally, we studied the process of steam humidification that, depending on steam temperature, may contribute to heating the air. Thank you very much for your attention. Goodbye.